You have assignments for me. Please send them to your left. I'll come up this side, I'll collect them all. If you've torn your stuff out of a spiral notebook, please take the fringes off. Make sure your name is on the page. I'll staple them if you haven't already. I'm not worried about that too deeply. Just send them to your left, please. At this point in time, the definition of a limit just basically says as x gets closer to a, f of x is getting closer to L. I'll come back. That's not a very precise definition. It's very hand wavy. We were looking at pictures, we were looking at tables. Close. I don't like this. One of the problems I have as a math person and as a geek, and maybe somebody along the spectrum somewhere, is that this is not a very precise statement. I want to know how close. How close is close enough? My idea is it really shouldn't matter. If we figure out how close you want to be to the limit, I should be able to find how close I have to get to that a value. An example. Please compute that limit for me. What's this limit? Because we take the numerator, factor it, things cancel. We can use that direct substitution where after we change the function because they match. But I know that function actually is undefined at 2. I know for a fact, you put 2 in there, that function goes. So how close do I need to get to 2 to be close enough to 4? First thing I need you to do is tell me how close is close enough. Okay, lab science people. Error in measurement is everywhere, right? And you will see in every lab report at some point, you'll talk about your error bars. But that means what you've done is decided what's an acceptable level of error and what isn't. I want to think of this the same way. What's my error I can use here? What do you think? How close is close enough to 4?
Technically, there could be like an infinite amount of decimal places.
Sure, but right now, here, right now, somebody tell me I think this is close enough. A tenth, a hundredth, a thousandth. What's an acceptable amount of error to be off of 4 by? You could literally pick any number. We're going to do a bunch of them, but somebody pick one. Okay, so within a tenth, 0.1. Suppose I claim close enough is plus or minus 0.1. So that means I could actually be anywhere between 3.9 and 4.1 and say that's good enough. So what I want to do now is, in response to this, say what you need to do is figure out what x's will make this true. Because then you can tell me how close I have to get to 2. If you tell me the range of x's that make this work, then you can tell me, okay, that range, and here's 2. We'll know on either side of 2 how far off we can be. I could do this algebraically. The algebra is not trivial, so I'm not going to do that at the moment. So instead of doing this algebraically, let me ask a question about what you think this picture might look like. Let's think about this graphically. That's the way we started our limit idea, right? Graphically. Graph for me the function x squared minus 4 over x minus 2. Now I know the graph is going to look really nice. What's the graph of this look like? It looks like a line because of the canceling we did when we saw the limit. So I get this picture. I really only care about what's going on near the point 2,4. So I'm going to change the window here. And I'm going to go from 0 to 3. And I'm going to go from 0 to 5 in the y's. So that I really only care about the point 2,4 where we actually have a hole in the picture. See, y equals blank. But I don't just care about this function. I care about the numbers 3.9 and 4.1 as well. Let's graph those. Graph of a constant, y equals 3.9. What's that look like? Y equals the horizontal line. 4.1 is going to be another horizontal line, slightly higher, right? So I'm going to create a strip. There's 3.9. There's 4.1. Please notice both of those values cross my graph somewhere. Where? Where does the graph of x squared minus 4 cross 3.9? I don't have to do any algebra. Say again? Around 2, right? Because 2 is here. So it's around 2. I'd like an actual value. So I ask the calculator, hey, where do these two graphs intersect each other? If you hit second trace, you get the calculate menu, which is where the calculator does stuff I want to know about. And option number 5 there is the intersection of two things. So I'm going to use number 5, and I'm going to say I want to know where the intersection of this first curve, if you hit enter, it leaves a little mark on that curve, and the second curve happens to be y equals 3.9. I hit enter there, and then it says, hey, give me a guess. At which point I just move my cursor with the arrow keys here closer to where I think they cross and hit enter a third time. That's exactly at 1.9. Do the same thing for the other one, please. This time, when you go to do it on the calculator and you say, where's the intersection, it'll look at the first curve will be the equation we want, but it automatically jumps down the list. The second curve is again 3.9. My 4.1 is the third equation in my list, so I have to hit the down arrow to jump to the next equation. Notice up there in the upper left corner, it says y3. That's my next equation. And then I can hit enter, and then I can go to where I think those cross, and I get 2.1. If my x value is in between those two, then the y value will be in the strip we created. So I now have an interval of x's. You want to be within 1/10 of the limit 4. I tell you, you need to be within 1/10 of 2 to hit it. My boss comes along and says, this isn't close enough. You got to get closer. So we move to a different, closer number. Let's say we did 0.01. I could do the same process again, right? 0.001. All right. We just pulled 0.01 out of thin air, right? I claim, no matter what number you give me for this tolerance, there will be another corresponding number that I can come up with to tell you how close you need to be to A. And I can actually think of writing this as x is 2, give or take 0.1. You told me how close I needed to be. I tell you how close you have to be. If a limit exists, then I can always do this. No matter what number you pick, I'll be able to come up with a corresponding one. the little tolerance we pick is going to be some positive number. I'm going to use that as my plus or minus up at the top. I'm going to call that epsilon. E. For any epsilon bigger than 0, there is some other number, delta. Also a positive number. So you give me the tolerance, epsilon. I give you back this tolerance, delta, so that if we are close enough to A, then the y value will be close enough to the limit. And this is really a bet. No matter what number you tell me, you have to be this close. I'll tell you how close my dialed in x value has to be. This is a pain in the ass formal definition. I could write it in formal logical symbols if I wanted to. We'll save that for another time. But this is a universal statement for any value of epsilon you give me, any positive number, no matter how small. Now, here is where a lot of people philosophically ran into a problem. Tay, I think you were saying it, although it might have been you, Emily, but infinite number of decimal places, Tay? Okay, here's a problem. If I give you 0.000000, infinitely many zeros and a 1, does that make any sense? So that idea of a number with infinitely many zeros after the decimal place and then a 1, you can't put something after infinity. This caused a huge philosophy fight between the people who were trying to say this worked and the people who didn't. They called numbers like that infinitesimals. They're so small, they don't really exist. Now, I will say with complete and utter sincerity, I think this is the most stoned idea I've heard of ever. There are numbers that are so small you can't see them. You can only write them if you write infinitely many zeros and then start writing the numbers. Ask me another one, man. You got to be kidding me. That doesn't make any sense. Infinitesimal arguments were put forth by Gottfried Leibniz and Isaac Newton. And between the two of them, Newton got in trouble because Newton was in England. There was this other guy in England, you know, the church, Archbishop of Canterbury, Bishop Berkeley. And Bishop Berkeley said, wait a minute. You want me to say that the vanishing ghosts of a departed quantity has an influence on the real world? You are consorting with ghosts. I claim you a heretic. And Newton wasn't allowed to publish in England. Leibniz was in Germany. He didn't give a crap what the Church of England said. So people used this because it worked. And they didn't care about the philosophy argument. But I want you to know it was there. And that's why it took 100 or so years to write this actual formal definition rather than the hand-wavy stuff. I like the picture. I like the picture so much, I'm going to try and use this in general. Page 107 of our textbook. I'm going to think about this epsilon as a vertical strip around the y value L. And then you'll see my graph crosses that strip. The top and the bottom line intersect the graph somewhere. So we're going to take those two intersection points, here and here. And we're going to go straight down to the x-axis. Now, if you look carefully, you'll notice that those are not the same distance from the point A. Which one's closer? Which one? The one over here on the right is closer to A than the one over here on the left. Okay, Think about standing at A and slowly moving your arms out at the same speed until you hit one of the walls. You're going to hit the right one first. I could go further on the left, but I definitely can't go any further on the right. So I'm going to say that this distance, that's my delta, the smaller of the two distances. And then I'll only allow myself to go that far on either side. I can go A plus delta or A minus delta. So now you gave me an epsilon, be this close, and I turn around and say, okay, well then here's how close you have to be to A. If you change epsilon, you're going to change the corresponding delta. This strip is narrower than this one. So this column is narrower than this one. But as long as I can always find a delta, it works. Let's put this to work and see if we can make this actually work for a couple of problems. Here is a problem from the textbook. Actually, it's from the old edition of the textbook, so the numbers might have changed in the new pictures, but the same idea is still here. I have a graph. I don't even know what it is. I have an epsilon value. Where is the epsilon in the description up here? A whole bunch of numbers in that line up there. Which one of them is epsilon? Perfect. I'm actually going to write that right here. Okay, wait a minute. This should also be an A and an L, and then I need to figure out what delta is, because that's actually given as a symbol, so I don't have to worry about them telling me what it is. Which one of the two remaining numbers is A, and which one is L? On the left. You mean this one?
Yes.
Yes, except the A itself is just the 1, because in our definition, it was x minus A. So A here is just 1, and that means that L is also 1. So take a look at our picture now, and let's see if that matches with what we were thinking. L is a y value, and then we have L plus epsilon and L minus epsilon, 1.2 and 0.8. Now we swing down to the x-axis. There's my A value. What's my value of delta? Starting at A, I start to spread out to the left and the right. Do I hit the left wall first or the right wall first? And so how far is it from the A value to the right wall? That's my delta. The distance from here to here. You found it. If the tolerance I am allowed is 0.2, then I need to be within 0.1 of my A value, 1. You'll pardon my bluntness, this seems useless. Where am I actually going to use something like this? Okay, who's in Gen Chem lab? You're measuring something. How many decimal places are visible on your scale? You need a gram. How close is close enough? Well, I suppose it depends on what you're putting in the mixture, right? If you're off by a a milligram of something, and that with a 4 decimal place scale, you get to tenths of a milligram, right? So if you're off by a milligram, is that going to make an effect on the actual reaction? I don't know. What are you reacting? How close is close enough? Now depends on the situation you're in. I couldn't actually bring it, but I want you to picture a bow and arrow. What do you aim for on the target? You aim for the very center, don't you? How many times do you actually hit the very center? I was watching an archery contest as a world's championship. And to give you an idea of how rare it is to hit the center, on the target, the center of the target is the lens of a camera. So they can look at the shot coming in. The one person who won the women's competition shot the lens twice in 12 shots. So I have a little bit of wiggle room. How big is that inner circle? You have the internet. Google for me. Diameter of the inner ring of an archery target. How big's the 10 ring?
centimeters.
12 centimeters. 12.2 centimeters is 4 inches. Okay, 5 inches. We'll run with 5 inches. I need 5 inches. 5 inches is almost exactly the length of a dollar bill. From 50 feet. That is your wiggle room. That's it. Hit this. But you're a human being, not a robot. So your aim is going to suffer from the fact that your arm moves. You let go of the arrow starts to wiggle. If you actually watch the flight of an arrow in slow motion, it bends back and forth. Why? Physics is a wonderful thing. When you let go of the arrow, the front doesn't start moving when the back does. So the arrow actually starts to squeeze. And so it bends. And then it starts to straighten out, and then it goes to bend the other way and keeps wiggling back and forth. Eventually, it will level out. Those vibrations slow down, and you hit the target. How much wiggle room do I have with my aim? Epsilon, delta. My movement. How close do I have to aim to the actual precise spot I want to hit to be within the 10 ring? So this idea is the width of that 10 ring, the 5 inches. This is the about 1/10 of an inch I have in wiggle room, or I'm off to one side or the other. Take this same idea, apply it to any situation where you actually have to draw something. Drawing with your pencil right now. If I asked you to draw a line 1 inch long and gave you a ruler with an inch mark on it, could you do it? How close would you get to an exact inch? How close is close enough? If I'm an architect and I'm making a scale drawing at 1 to 168, if I'm off by 1 inch, that drawing is off by 168 inches. If I'm building a building or a railroad or a tunnel through the side of the mountain, and I miss by 168 inches, we have a problem. Computer chips are made on disks of silicon. So in order to make a computer disk, you first have to make a circle of silicon. I need a disk with an area of 1,000 square centimeters, so I can put enough computer chips on it. So, question for you. What's the radius of the disk? Formula for the area of a circle. Say again. I think you're off by a factor. One circle is 1 pi r squared. The 2 was the cylinders, top and bottom circle. I only need 1 pi r squared. So what I want to know in order to solve this problem is what's the radius so that pi r squared is equal to 1,000. Find me that radius. Little bit of algebra. Gives me this, right? There's just one problem. This number sucks. Now, I am going to be a pedantic mother. I'm writing down every one of those decimal places. Because technically, this is an irrational number. It should never terminate. It should never repeat itself. This number should keep going on and on and on with more decimal places, however many I want. I'm going to write all 8 of these decimal places for the moment. Eight, 4, 1, 2, 4, 1, 1, 6. If your calculator goes out in more decimal places, write them all down for right now. What does part B tell me? Oh, there's some allowable level of error. But the error is not in the radius. The error is in the area of the disk. Machinist is allowed an error tolerance of give or take 5 square centimeters. 5 square centimeters. So I could be as big as 1,005 or as small as 995. What are the radii that do that? Oh, wait a second. Wait a second. All I have to do is do this again. But now I have to do it for 1,005 and for 995. The numbers aren't all that hugely different, are they? Again, I'm going to write down all the decimal places. But those are unfortunately not the answer to my question. Because the question actually asked, how close to the ideal radius from part A must the machinist control his radius? In other words, how close to this number is close enough? Which means I need one more piece of information. I need to know how far apart these are. I need to know how far apart these are. Now, one's positive and one's negative, but I really don't care about what sign the number is. I just care about the size. So I'm going to think about ignoring that minus sign. Take the absolute value in both cases. Which one of those numbers is smaller in absolute value? Aha. 4454 versus 446. Okay. So if you tell me that I have a leeway of up to 5 square centimeters of area, then when I adjust the dial for the cutter to cut the circle, when I adjust the radius, I can be off by no more than 0.0445 centimeters. Wait a minute, that's 4/10 of a millimeter. Less than half a millimeter of leeway. The dial on that radius better be really precise, don't you think? Let me think about this as a limit definition. What number in this problem played the role of L? What was our target? The first radius was the thing I needed to aim at, but I want to know the output of that, because remember, this is a y value. I suppose it would help if we wrote down what the function was. So what's my function? Aha. I'll write it in terms of x because we wrote everything in x in the problem, in the definition. So if I think of that as the function, then the L should be an output of that function. What was the ideal area we were aiming for? 1,000. The 17.8412, et cetera, that was where I needed to aim to hit it. That's my A value. What's epsilon? The amount of permissible error in the y value. The 5. I don't care about the plus or minus, I just care about the number. 5. These are in the same unit, square centimeters, square centimeters. And now we figured out up here the value of delta. What is the allowable error in A? Oh, it's this number right here. 0.04454749. And these are in the same unit. These are in centimeters because I'm controlling radius, and then I'm going to let the cutter cut the circle. I don't know what your eventual future job will be. I have no idea where you're going to go from here. But as a lab scientist, bench hands are an important thing. Being able to get the measurements right, understanding the equipment, and how close I can actually get to tolerance on any particular thing. I would love to tell you this is useless. I don't want to make silicon wafers for making computer chips. I want to make rebar for building buildings. What's the appropriate diameter of rebar for a concrete floor? Round here, state regs say I think it's 3/8 of an inch. If you're under and you put the wrong rebar in the concrete, what happens? The floor goes bye-bye. I'd like not to die, people. I'd love to tell you this is useless shit, and you're never going to need it. But any job you do that has some level of precision to it allows you a little bit of leeway in your accuracy. And as long as a limit does exist, then I should be able to tell you what my tolerance is for both of those things. I did say we could do this algebraically, but doing this algebraically requires me to then solve the algebraic equations that we did in the intersections by hand. I'd have to do those mathematically. So if I was looking at, say, the function is x cubed, and I want to show that the limit as x approaches 2 of x cubed is 8. You might say to yourself, well, that's direct substitution. That works. At which point, the geek in me goes, prove it. Okay. How close is close enough to 8? So again, 0.1 for tolerance. I'm going to say, all right, if you want me to be within 0.1, how close do I have to get to 2? Well, that means I need the absolute value of x cubed minus 8 to be less than 0.1. Now, my eventual goal is to turn that algebraic expression from this involving f of x to this involving just x. So I'm going to rearrange and do a little algebra light here. And I'm going to say, all right, if I need to be within 0.1, I could be as small as negative 0.1 or as big as 0.1. That's how far off I'm allowed to be. Add 8 to all the sides. 7.9 less than x cubed less than 8.1. And now take a cube root. What's the cube root of 7.9? There is a cube root button on the calculator. It's hiding under the math menu. If you hit the math button, third button on the left side, there's a cube root right there. But you can also use a 1/3 power. Remember, we said that powers and roots went together. So I need the cube root of 7.9, lots of decimals.
not what we used to.
Not, why is it not what? Well, because back in my original definition, they were strictly less than. I can use less than or equal to if you want. I have to go back and look at the definition. It said strictly less than, be within this tolerance. That means inside it. 1.9916311701. Less than X. Less than, I need the next number. 2.008. And now I say to myself, this is great. How close are these numbers to 2? Subtract 2 across the board. Oh, there's 2 zeros. By the way, that's the left edge bar. That's the right edge bar on either side of 2. So now I can ask, which one do I hit first? The one on the left or the one on the right? As I start to move out. Bethany? The right. 0.00829 is closer than 0.00836. So this value, that's going to be my decimal because it's smaller. So that's how close I need to be. Please notice, you said I only needed to be off by 0.1. I need to aim to within 0.008. Pretty, really small, isn't it? The more complicated the functions get, the less pleasant the algebra gets. If I wanted to do this for something like e to the x, I'd have a logarithm floating around somewhere in here. If I wanted to do this for a square root, I'd have to square to get things out. The algebra itself is a pain in the neck. So how often do you think I'm going to make you do something this disgusting and ugly? This homework assignment, and then you forget about it. But understand, this is the deep idea under limits and therefore under derivatives and integrals, and everything else you're going to do ever in calculus is based on coming to a definition like this. How close, how small. Calculus at its heart is the study of infinitely small, infinitely large things. So really getting my hooks into understanding what infinitely small things look like is important. All of the results you see us use had to be proved in terms of those random letters, epsilon and delta. And those are the arguments that underlie mathematics. It's not, does it work? That's engineering. That's science. Why does it work? That's math. I will see you all on Monday. I hope you have a wonderful weekend. If you came in late, if I don't have your homework, please come give it to me. Otherwise, I will post the keys after I finish the grading. See you Monday. Well, I got everybody here, and I got the seating chart. So I just looked around and said, who's here?